Hello everyone, welcome to this video. So in this we'll learn about how to calculate sums of these kind. These kind of sums are called power sums. Uh, so so how we'll do the proof? First we'll note a very nice observation about these sums, and then we'll try to prove this observation, and as part of the proof we'll find a method to calculate the formula for this sum. So the observation is the formula for this sum is a polynomial of degree n plus 1 in M. What we mean by that is that the formula of this sum will look like a naught m power n plus 1 plus a1 m power n plus a2 m power n minus 1 plus dot 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 plus up to an plus 1. Cool. Of course, in the actual formula, when we find the formula for this sum, this a naught, a1, a2, they will not be variables, they will be some values. But if you try to find a formula for this kind of sum, it will look like this. And this formula is helpful because uh, let's say uh, let's say the power is small. Let's say we're trying to calculate I don't know, the fourth powers, 1 power 4 plus 2 power 4, but we want to know the value of the sum for a very large number, let's say 1 million. So this becomes very easy because there are only n plus 1 terms. There are only 5 terms in the formula. So that's why it's better when we want to find the sum for a big M and let's say the n is not that big. So let's try to prove this claim, and as part of the proof we'll see that we'll also find a method of how to calculate these things. So for proof we'll use mathematical induction to prove this. Mathematical induction is a fairly common technique which is used uh, in a lot of proofs related to maths. Uh, you can go ahead and try to watch YouTube videos or read online about it if you don't know. But it's a fairly common technique, and you'll find a bunch of resources online. So in mathematical induction, what we do is we first prove the base case, which is let's try to prove it for power 0. So the sum looks like 1 power 0 plus 2 power 0 plus 3 power 0 dot 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 plus m power 0. So it becomes m. Now m we see is a polynomial of degree 1 in m, which is 1 more than the power. Hence, the base case is true. So now as per mathematical induction, the next step would be uh, that we assume that the claim is true for all powers less than equals to n minus 1. That means for all powers less than equals to n minus 1, the sum is a polynomial of degree 1 more than the power. Now we assume this. This is the second step in mathematical induction. Now let's move to the actual case and try to prove this for the power equals to n case. Now there's a very neat trick that we use to do this proof, and that is basically we write the binomial expansion of, let's say, k minus 1. And why we do that you'll notice very shortly. Uh, so The binomial expansion of this looks like r equals to 0 to n plus 1, n plus 1 cr into k power n plus 1 minus r into minus 1 to the power r. So let me write the sum here as well so you can easily see that what we were trying to find. Now if you see these power n's, a term with power n will appear here. And the idea is if we sum over k from 1 to m, it will look exactly like our sum that we have to find. So this is one of the uh, reasons you can see like why we use the binomial expansion of this. But slowly we'll see like why we did it, because uh, it will be very easy to calculate this when we expand this a little. So let's first expand first two terms here and leave the rest of the formula here, and we'll see why we are doing that, because ultimately we want to introduce s in this equation. So k minus 1 to the power n plus 1 equals to, let's see the first term here. So the first term r equals to 0, so this term will become n plus 1 c 0, which will be 1. This term will become k power n plus 1 minus 0, which will be k power n plus 1, and this term will be 1. So the first term here will be k power n plus 1. Now the second term here would be n minus n plus 1 into k power n, and let's see how it is. So this part will become negative 1 because r is 1. Then this part will become k power n, and this part will become n plus 1. So we see that is true, and let's write the rest of the term like this. Now r will start from 2 because we already expanded the first two terms. K power n plus 1 minus r into minus 1 to the power r. Now since we have to deal with this term when trying to introduce s in the equation, let's bring it to this side and this to this side just for the ease. N plus 1 into k power n equals to k power n plus 1 minus k minus 1 power n plus 1 plus, I'm rewriting the formula once again, nothing fancy. Now let's sum both sides from k equals to 1 to m. Since we are doing it on both sides, it's equal. Plus summation k equals to 1 to m, summation r equals to 2 to n plus 1, and due to lack of space I'm writing this here, which will be n plus 1 cr k power n plus 1 minus r into minus 1 to the power r. Now this n plus 1 doesn't depend on k, so let's move this out of the summation. It's like taking common, and if you see we are summing from 1 to m, so this part will become 1 power n plus 2 power m, n plus 3 power n plus 4 power n up to m power n, and we notice that this is our sum that we need to find. Now this becomes, now if you carefully look at this term and let's try to expand it from top to bottom. Let's try to first see what this term will look like when k equals to m power n plus 1 minus m minus 1 power n plus 1. Similarly, for m minus k equals to m minus 1, this will be m power n m minus 1 power n plus 1 minus m minus 2 power n plus 1. Now, for the next term, m minus 2 power n plus 1 minus m minus 3 power n plus 1 plus dot 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 2 power n plus 1 minus 1 power n plus 1 plus 1 power n plus 1 minus 0 power n plus 1. Now if you carefully look, these terms will cancel with each other. Everything here. And we'll be left with just two terms. 0 will be just 0, and this is the only term left. Now, and let's see the second part of the summation. And since it is a double summation, we just reverse the double summation because it really doesn't make any difference, because we'll be ultimately summing the same thing just in different order. So r equals to 2 to n plus 1, k equals to 1 to m, n plus 1 cr k power n plus 1 minus r into minus 1 to the power r. Now let's write the formula once again. N plus 1 into s equals to, this term will become m power n plus 1 plus, now we see that this term doesn't depend on k and this term also doesn't depend on k, so let's take them common and bring them out of the inner summation. To n plus 1 cr into minus 1 to the power r summation k equals to 1 to m k power n plus 1 minus r. Now uh, now notice one thing, that once we fix r, this again become power sum. Power sum. Only the powers are, power is not n, but the maximum power, here is when r equals to 2. So then the power will be n plus 1 minus 2, which will be n minus 1. But as per mathematical induction, we already assumed that for all powers less than equals to n minus 1, our claim will be true. So it means this sum uh, is a polynomial of degree 1 more than this, which will be n in m. And since it is the highest, it is the maximum power here, all the other power sums will have lower degree than m. So this whole term will have degree n, or let me write it in better words. Whole of this will be a polynomial of degree n, and this term has degree n plus 1 in m. So ultimately this whole right hand side, this becomes, this whole right hand side, this becomes a polynomial of degree n plus 1 in m. And this is just a constant, so rs, the sum, our power sum, is essentially a polynomial of degree n plus 1 in m. And now since we already proved this, so this is proved. This is how it is done. We'll carefully look at the proof once again, but ultimately the thing that we notice here is this formula gives us a way to calculate s as well. This gives us a way to calculate s. So let's first quickly go over the proof once again, and then we'll utilize this formula to calculate power sums for maybe let's say just one power and see if it holds true. So let's quickly jump up. So let's see. So let me grab the pointer. Yeah. So we have to find sums of these kind. These are called power sums. 1 power n plus 2 power n plus 3 power n up to m power n. Now one observation that I just told you is the formula for this sums is a polynomial of degree n plus 1 in m. What that means is it will look something like a naught m power n plus 1 plus a1 m power n plus a2 m power n minus 1 dot 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 up to a n plus 1 n plus 1. So of course, like these will not be variables, these will be the coefficients, and that's the aim. That is our aim, to find these coefficients. So first let's prove that this claim is actually true. Like why should we just agree that hey, this is a polynomial n plus 1, because this doesn't seem obvious. So to prove this, we'll use mathematical induction. It's a fairly common technique. You can go and read about it if you already don't know about it. So let's first try to prove the base case. That is the first step in mathematical induction, and let's try to prove it for power 0. For power 0, the sum will look like 1 power 0 plus 2 power 0 plus 3 power 0 plus dot 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 m power 0. These are just power 0 means this is just 1 added m times, so it will become m. And we see this is the polynomial of degree 1 in m. And as per the claim, it should be the sum should be a polynomial of degree 1 greater than the powers. So it is 1 greater than the power. So the base case already holds true. Now, as per the mathematical induction, the next step is we assume that this claim, our claim holds for all the powers less than equals to n minus 1. So for all powers less than equals to n minus 1, we assume that the sum is a polynomial of degree 1 more than the power. So we assume this. Now let's see for power equals to n step. Let's try to prove this. Now the trick here is that we'll use the binomial expansion of k minus 1 power n plus 1. And why we are doing this is because ultimately power n will appear in the binomial expansion of this, and if we play smartly and sum over k equals to 1 to m, we'll make this s in this formula somehow. And the other benefit of using this is power n plus 1 is the uh, the power of n plus 1, you'll see there this term will automatically cancel out, uh, and this and for choosing power n plus 1 makes sense also because the claim that we are trying to prove is this should be a polynomial in n plus 1. So it makes sense to start with this and then try to see like if we can really like try to make a formula out of this, if we are really able to make a formula out of this. So basically if we expand the first two terms here is uh, the first term here will look like k power n plus 1 because this part will become 1 and this part will become 1. So k power n plus 1 minus the second term here would look like this will become minus 1 because r is 1. This will become k power n and this will become n plus 1. And this is what we have written here. And we leave the rest of the summation as it is. Now we move this term here and this term here just for the sake of convenience and easy to visualize the equation. So just moving it around here, this equation will look like this. Now we sum over k equals to 1 to m. Now if you carefully notice this part summing k equals to 1 to m become s. N plus 1 is just a constant because it doesn't depend on k. We can take this common and we do the summation on the right hand side as well. Now for the right hand side, now this becomes n plus 1 into s, and from the right hand side if we carefully expand this, we'll see all the terms will cancel with each other. Just the final term from here and the bottom term from here will be left. So it will be m power n plus 1 and the here it will be left is 0 power n plus 1, which is 0. So m power n plus 1 will be left. So and the second part here is, since this is a double summation, we'll reverse the order of the summation because it doesn't matter. We are adding the same terms just in different order, and we'll see why we did that. So we just reverse the order, and in the next step we see this term and this term doesn't depend on k, so we take them common out and we are left with summation k equals to 1 to n m k power n plus 1 minus r. Now if you see this, these are again power sums, just the powers are power is n plus 1 minus r. So once we fix an r, this power remain constant and this is just a power sum. And what will be the maximum power sum here, like the maximum power in the power sum here? It will be when r equals to 2, which will be n minus 1. But as per mathematical induction, we already assumed that our claim holds true for all powers less than equals to n minus 1. So it means for this, when power equals to n minus 1 and even lower, the claim will hold true. So all this is a polynomial of degree 1 more than the power, which is n in m. And when r is bigger, the power is smaller, so obviously it is a polynomial of degree less than n. So this whole thing is a polynomial of degree n in m. and this term we see has degree n plus 1. So this whole right hand side becomes a polynomial of degree n plus 1 in M, and that was our aim, to prove that the sum S is a polynomial of degree n plus 1 in M, and this n plus 1 is just a constant, so it doesn't matter. So we proved that this S is a polynomial of degree n plus 1 in M. Now let's quickly try to use this formula, because we did the proof, but this proof also gave us a way to find the formula for S. Now, uh, now let's choose like some value of n. Let's say we are trying to find the power sum where n equals to 1. So we are trying to find the formula for this sum. So if you already know, the formula for this sum comes out to be this. This is a very common uh, sum in math, and we already know, and there are a bunch of other easy ways to calculate this formula as well for power 1. For higher powers, there are not many good ways to calculate that, but for n equals to 1 we already know that this is an easy way. Now let's try to apply this formula for n equals to 1. So for n equals to 1, this will become 2 into s equals to m square plus r goes from 2 to n plus 1, which would be 2, so there will be just one term. So let's just write that term. N plus 1, this will become 2c2 into minus 1 square into k goes from 1 to m, k power n plus 1 minus 2. So n is 2, n is 1, so 1 plus 1 is 2, 2 minus 2 is 0, k power 0. So this is what it looks like. Let's simplify it. 2 into s equals to m square. 2c2 is 1, minus 1 square is 1, and this is summation k equals to 1 to m over 1, k power 0 is 1. So this is just adding 1 m times, so this will become m. So this will be 2s equals to m common m plus 1, and this becomes s equals to m into m plus 1 divided by 2, and you see this matches. Here let's make it m only, so it becomes clearer. Let me erase and write it again. So let's sum till m only here, and let's write the formula as m into m plus 1 by 2. So you see, this matches with the formula, so it gives you some confidence that this is actually true. So as a fun exercise, what you can do is you can try to find the formula for n equals to 2 using the same formula. I can tell you, we already know that this sum comes out to be m into m plus 1 into 2m plus 1 divided by 6. What you can do is you can try to apply this formula only, and try to find the formula for n equals to 2 and try to match that if this comes up to be this. Thank you guys. Yeah, that's all for today. I hope you enjoyed this video. You enjoyed the video, and I would recommend you to watch it once again. Just go over the basic steps, and in the last, try to find a formula for this on your own. Uh, so uh, yeah, that's all for today. In one of the future videos, I'll tell you one more way to calculate these power sums. There's one different technique as well in which we can calculate these power sums. That technique also relies on the idea that this power sum is a polynomial of degree 1 more than the power. That's why I proved this in this video, but we'll try to see a different method of calculating these sums. Um, and till then, see you. Have a good day.